Okay, good morning, everybody. So the plan for today is to finish up Chapter 6 with Section 6.7, Integer Exponents and Scientific Notation, and then starting the Chapter 7, Factoring, with Section 7.1, Greatest Common Factor, and Factoring by Grouping. The quote of the day today, I was hanging out with some friends over the weekend, and one of my friends mentioned that her daughter is going on a phone fast for Lent. So some people like give up things around this time of the year, and some people give up sweets or junk food or try to exercise more, something like that. But what she did is she actually went out and bought an old school flip phone, like a dumb phone, and put her smartphone away and is only using the dumb phone so that she's spending less time on her phone. So that kind of reminded me of this quote from Peter Arve, the co-founder of Prezi, the presentation software, where he says, "The concept of always being reachable makes us present nowhere." And I think that's so true today. We have so many, things pulling at us from all directions, seemingly all the time, whether it's social media or texts or, even like notifications from apps constantly trying to get us to open them up. It's sometimes hard for us to be present with the people that we're physically in the same room with. So, uh, just a thought for, especially with things like spring break coming up in a couple of weeks, maybe being able to take a little bit of time to disconnect a bit when you don't have to be checking your email quite as often for school or anything like that. So that is the quote for today. Sorry, sorry. Okay, so we're continuing on with section 6.7, which we started last time. And remember, for this section, we're assuming that all of our variables are non-zero, so we're not like explicitly writing out, x can't be 0 and y can't be 0 at the end of each of these. That's assumed for this whole section. And just a quick recap of these two examples that we did last time, and then we're going to move on to two similar exercises. So here we're looking to simplify x squared over y cubed all to the negative 2 power times x cubed y. And we have two factors here, and it's probably good to kind of start with this first factor. It looks kind of complicated. Let's work with it and simplify it a little bit first. So maybe I'll come off to the side here and look at x squared over y cubed to the negative 2 power. And the first thing I might realize is I have something to a power, but I have something to a negative power. That means I can write 1 over that thing, or in other words, flip the fraction, make it y cubed over x squared to the positive 2 power. I suppose I could have distributed the negative 2 power itself and then done all the flipping, but then I would have had to flip multiple things over the fraction line. And I think it's maybe a little less error prone, a little cleaner to do it this way. But if you had done it that way, that wouldn't have been incorrect, as long as you were careful with all of the operations. But now I see I have a quotient to a power. I have a over b to a power. So that is the numerator raised to the power divided by the denominator raised to the power. And here's where, like I said, if you had distributed the negative 2, that would have been fine as well. You would have just had more things to flip in the next step here. And in my numerator, I have power to a power, y cubed all squared. That is y to the 6th power. I multiply the powers. And in the denominator, x squared, I multiply the powers again, 2 times 2, x to the 4th power. Okay, so this whole thing becomes y to the 6th power over x to the 4th power. And I'm multiplying that by x cubed times y. And there's a couple approaches I could take here. I could kind of combine everything in one fraction and then simplify. But I think what I'm actually going to do here is I'm going to rewrite this y to the 6th over x to the 4th as y to the 6th power times x to the negative 4th power. That x to the 4th in the denominator can come up top as x to the negative 4th. Again, multiple ways to go about this, but I'm doing this for more illustration with the negative powers. And then times x cubed y, but that's really just times x cubed times y. And if I really wanted to be very clear about what I'm doing, I can have x to the negative fourth times x cubed, bring those out in front using the commutative property of multiplication, times y to the sixth times, and then this y, just to be very clear, I'll write it as y to the first power. Now I have a product of the same base to different powers, or to some powers. I keep the base, I add the powers. Negative 4 plus 3 is negative 1. And the same thing here. Y to the power 6 plus 1, or y to the 7th. And I could either leave it like this, or oftentimes when we want to fully simplify something, a lot of times we want to get rid of all the negative exponents. So I might write this as y to the 7th power over x to the first power, or just over x. So often WebAssign will instruct you something along the lines of, you know, write everything in terms of positive exponents or something along those lines, and you'd want to write it this way then. But I think, as far as if you were using this as an intermediate step to solving a problem or something, I think it's a coin flip which one is simpler, which one is more is easier to use in different cases. Okay, and then we did look at this as well, so this should be a little bit of review as well. We want to remember that when we're raising something to a power, really the only thing that gets raised to the power is the thing that's immediately under the power. So in this case, it's really just the x that's getting raised to the negative 2 power. This is basically like negative 3 over x squared. This one, the whole 3x, is getting raised to the negative 2 power. So this is like negative 1 times 3x to the negative 2. Or it's like negative 1 over 3x all squared. Or that's like negative 1 over, I have 3 times x to the second power. That's 3 squared times x squared, or 9x squared. And then for the third one, it's actually the whole negative 3x that's getting raised to the power. So negative 3x all to the negative 2 power is 1 over negative 3x squared. And here I have like negative 3 times x to a power. So I have a product to a power. So that's 1 over negative 3 squared times x squared, or that is 1 over 9x squared. So this last one is positive 1 over 9x squared. The middle one is negative 1 over 9x squared. The negative didn't get squared in this case. And the first one is just negative 3 over x squared. The negative 3 wasn't affected by the power. So we do have to be careful to recognize what is actually being raised to the power and what is being multiplied on in front of the thing being raised to the power. Okay, so let's work through these two exercises. Maybe it will take about 4 minutes or so. Take your time, work through it carefully. Don't try to rush it, especially with this one down here. So take your time. We'll take about, yeah, maybe about 4 minutes, I think should be enough for these two. So we'll come back in 4 minutes and discuss the answer. Okay, let's talk through these two. It's a little over 4 minutes. So for this first one, again, I look at this problem and I see that I have the product of two things. And the first thing's a little complicated, so let me work on that one first, although this one's a little easier than the previous example. So here again, I have the -1 power, x cubed over y squared to the -1 power. So I'll flip the fraction, make it y squared over x cubed to the +1 power. And of course, with a +1 power, I just don't have to write it. And now I want to do the multiplication here. And here I kind of in one step, I rearranged things as well as wrote everything kind of up in the numerator. So I made the x cubed into an x to the -3. The x squared can come in front of the y squared. This y squared came down and this one did as well. Everything's multiplied together. We can move things around to get all of our kind of similar bases together. And then we see that we have x to the power -3 plus 2. Well, -3 plus 2 is -1. So that's x to the -1 power times y to the power 2 plus 2, y to the 4th. And if we wanted to write that with positive exponents, we would write it as y to the 4th divided by x. The x to the -1 goes into the denominator as an x to the +1. All right, so looking at this next example, we have 3 different examples where some stuff is raised to the -3 power. For the first, negative of 2x to the -3. Well, that's really like -1 times 2x to the -3. Or that's like -1 over 2x cubed. Or -1 over 2 cubed times x cubed, or -1 over 8x cubed. I think that's probably the trickiest one. This one here, -2x to the -3, well, that -2 is really just multiplying x to the -3. Or it's really just -2 divided by x cubed. And then the last one, -2x all to the power -3. Well, that's like 1 over -2x all to the third power. So that negative exponent can put the whole base in the exponent, make it a positive power. And then I can think of this as like -2 times x, the product of two things, all to the third power is -2 cubed times x cubed. -2 cubed, -2 times -2 times -2 is -8. So I have 1 over -8x cubed, but that's the same thing as -1 over 8x cubed. We actually get, curiously, the same answer for the first and the third example here. Did we make a mistake? Well, no, actually what's happening is because this is a cubed, since it's a third power, since it's an odd power, whether the negative sign is inside or outside actually doesn't matter. Because, for instance, -1 cubed is just -1. It did matter in the previous example because we had an even power, and because -1 squared is +1, not -1, the square gets rid of the negative. So if the negative's inside the square, it's gotten rid of. If it's outside the square, it remains. With a cube, it actually kind of doesn't matter. If it's inside or outside, the negative, whether it's inside or outside of the cube, it still sticks around at the end. So, so because we had an odd power here, that's why it, our -1 stuck around here because it was outside of the power, but the negative being inside the power still sticks around if it's an odd power. So that's why those two ended up being the same answer. Okay. But note that that's not to say that these two notations are really saying the same thing, right? In this case, when I simplify this and simplify this, I get the same thing, but that's not saying that in general, It doesn't matter if the negative is inside or outside, right? Just to be clear, up here we saw that it certainly did matter. We got a different answer. So. Okay, so let's move on to scientific notation. This is maybe a little bit of a digression from what we've been talking about, things like polynomials and so on. But I think it's one of those things that it's good to have somewhere in your mathematical career, right? You've probably covered this in, a chemistry class, maybe a physics class, maybe just kind of an intro like science type class. So what is scientific notation? So let's just start by recognizing something here, that we could take the number 351 and as a little aside, pretty much the only time that I will refer to the times operation with something that looks like an X is in scientific notation. So we can refer to 351. We see that that is the same thing as 35.1 times 10, right? The 10 would just, if I multiplied it into the 35.1, it would just bump the decimal point 1 to the right, making 351. Or I recognize that this could be also written as 3.51 times 10 squared, or 0.351 times 10 cubed, or 3,510 times 10 to the negative 1, right? I realized that I could take any integer, for instance, move the decimal point left or right, and multiply by the appropriate power of 10, and I would get a different way of denoting the same number. And that's not even, necessarily, it's not even necessary that we have an integer here. We could really do this with any number. We could move the decimal point one place this way or one place that way. As long as we multiply by an appropriate power of 10, we're in the clear. So I have lots of different ways of referring to the same number, right? Even more than I've written here. What's the idea of scientific notation? Well, let's start with the definition. We say that a number is written in scientific notation when the number is written as a times 10 to the k power, where a is between 1 and 10 in absolute value. In other words, what we mean by that is there's exactly one non-zero digit to the left of the decimal point, and k is an integer. So if I look up here, well, 351 is kind of like 351 times 10 to the 0 power. But here my a, 351, is certainly not between 1 and 10. 35.1 is not between 1 and 10. But 3.51 is between 1 and 10. So this version of writing the number is the one that's in scientific notation, 3.51 times 10 to the second power. Now, why do we do this? This seems like kind of a silly thing to do, right? Why not just write it as 351? Well, when we're working with numbers that are either very large or very small, which often happens in the sciences, you think of chemistry, like, what's Avogadro's constant, like something times 10 to the 23 or something like that. Like, that's a huge number of individual atoms or particles or whatever in, whatever it is, 1 mole of some substance. Some small amount of some substance has a ton of individual atoms or molecules, whatever it is, in it. So if we're working with numbers that are very, very large or very, very small, not numbers like 100 or 1,000 or 1/10 or 1/100th, but numbers much larger or much smaller than that. Or whenever we're working with numbers that have very different sizes. This allows us to quickly determine the size of the number by looking at the exponent on the factor of 10, by looking at the k up here. I look and I see 10 squared next to the 3.51, and I see, okay, this is like in the ballpark of 100. 10 squared is 100, right? So 351, it's like, it looks kind of like 100. It's not like, in the like millions or billions, and it's not like in the thousandths or something like that. It's like in the ballpark of 100. So if we're looking at, say, something like the rest mass of an electron, 9.1 times 10 to the negative 31 kilograms, which is how nobody would actually present it, but that's what it is. Um, that's a much easier way to say this than point a whole bunch of zeros, 9.1 kilograms. Like you have to sit here and, mark off with your pen. Like there's 3, there's 6, you'd have to sit there and count all of the zeros if somebody wrote it that way. But if I say 9.1 times 10 to the negative 31 kilograms, I know that, oh, okay, it's about 10 to the negative 31 kilograms. If I look at the rest mass of a proton and I see that it's like 10 to the negative 29 kilograms, I know that a proton is about 10 squared uh, as massive. It's about 100 times as massive. Or maybe I see that the approximate diameter of the observable universe is 8.8 times 10 to the 26 meters. Again, that's a much nicer way to write this than to say 8 and a whole bunch of zeros meters. Okay, so writing 351 in scientific notation. So I want exactly one non-zero digit to the left of the decimal point. So I want 3.51. Now to do that, I had to move my decimal point 2 places to the left, but I don't want to change the value of the number. So to account for that, to kind of move it 2 places back to the right, I multiply by 10 squared. Is it true that 351 is like 3.51 hundredths? Yeah, that's true. If I look at, say, 14,375, I need to move 1, 2, 3, 4 decimal places to the left to get 1.4375. I moved 4 decimal places to the left, and to account for that, I then need to multiply by 10 to the fourth. Is it true that 14,375 is like 1.4 or so 10,000s? Yeah, that makes sense. It's a little above 10,000. What about a number like 0.007? This is a small number. I have only a 0 to the left of the decimal point. I need to move my decimal point 1, 2, 3 places to the right to make 7 times. I move 3 places to the right, so I need to multiply by 10 to the negative 3 to kind of counteract that, to account for that, to move the decimal point 3 places back to the left. Or another way of thinking of it is, by moving 3 places to the right, I've multiplied by 10 cubed. And to not change the value of my number, I need to then multiply by 10 to the negative 3. So 10 to the third times 10 to the negative 3 just makes 1. So we have 7 times 10 to the negative 3. Or if we have a negative number like negative 37.41, well, we basically do the same thing. I move my decimal point 1 to the left. I get negative 3.741 times 10 to the first. I moved my decimal point 1 to the left, so that was like multiplying by 10 to the negative 1. So I need to multiply by 10 to the first to counteract that. Or negative 0.00034. I want this to be 3.4 times 10 to the something. I had to move 1, 2, 3, 4 places to the right. So it's got to be times 10 to the negative 4 to counteract that. Basically, in moving 4 places to the right, I've multiplied by 10 to the fourth. I need to divide by 10 to the fourth, or multiply by 10 to the negative 4. That's a 4, not a 9. to account for that. And oh, and that's negative. And we can go the other way as well. We can move from scientific notation to decimal notation. 7.21 times 10 squared. Well, this is an operation that we've done many times in the past. We just multiply by powers of 10. That just means moving the decimal point so many places, one direction or the other. So multiplying by 10 squared, we move 2 places to the right, 721. Does it make sense that 7.21 times 100 makes 721? Yeah, that makes sense. It's always good to do kind of a reasonability check just to make sure you didn't move the wrong direction or something like that. 7.21 times 10 to the negative 1. I need to move 1 place to the left. 0.721. Is it true that 7.21 over 10 is about 0.7? Yeah, that makes sense. 7.21 times 10 to the fourth. Here I need to move 4 places to the right. I actually kind of run out of places, but I can kind of reimagine this as 7.2100. I can append zeros to the right when I'm on the right side of the decimal point and to the left when I'm on the left side of the decimal point as needed. And now I can move 1, 2, 3, 4 places over. So that's times 10 to the fourth still. Moving 4 places over gives me 72100. And let's put a comma in there after the 72. So 72,100. 10 to the fourth is 10,000. I have about 7 10,000s or about 70,000. That looks like the answer that I got over here. So it seems like I went the right direction. And similarly, 3.09 times 10 to the negative 3, I want to go 3 places to the left. But again, I kind of run out of places to move. But I can think of this as like 003.09 times 10 to the negative 3. And now I can move 1, 2, 3 places to the left. So I have 1, 2 zeros after the decimal point, then 309. I also kind of appended this initial 0 here. I don't particularly like to start numbers with a decimal point. I don't like to write 0.5. Actually, I had to really think to write that because I'm so used to writing it the other way. I like to write 0.5. And the reason is that it's easy to just miss the decimal point at the beginning there if there's nothing written in front of it. It sticks out a little more if you have a 0 written in front of it. Okay, so let's take about 3 minutes or so and work through these 2 exercises. I think these should be pretty quick to work through, but sometimes putting numbers in scientific notation can be a little tricky. So when you do write your number in scientific notation, take care to kind of check and make sure that what you've written does kind of make sense. Like we did up here, like we said, 0.007 is 7 times 10 to the negative 3. 10 to the negative 3 is like 1 over 1,000. Is this like 7 thousandths? Yeah, that looks correct. If I wrote 7 times 10 to the plus 3, 10 to the plus 3 is like 1,000. That would be saying that this is 7,000. And no, I went the wrong direction there. Okay. So take about 3 minutes, work through these 2 exercises, and then we'll discuss the answers. Okay, it's just about 3 minutes, so let's take a look at these. Okay, so for 100, we want to, well, we imagine the decimal point being at the very end of the 100, so it's like 100 point or 100.0. We want to move the decimal place 2 places to the left so that I have just a 1 in front of the decimal place. And this is 1 times 10 squared, or if we wanted, I guess we could write it as 1.0 times 10 squared. So negative 0.152. Well, here we need to move the decimal point 1 place to the right to get one non-zero digit in front of the decimal. So that's negative 1.52. And then to account for that, we have 10 times 10 to the negative 1, or 16,589. We think of the decimal point as being at the very end of that integer. And we need to move that 4 places to the left between the 1 and the 6 to get exactly one non-zero digit in front of the decimal point. So we have 1.6589. And since we moved 4 places to the left, we need to multiply by 10 to the fourth to counteract that. And the second exercise, 3.995 times 10 squared. 3.995 is pretty close to 4. So this should be like 400 or so, 4 times 100. And I do see that if I move my decimal point 2 places to the right, I get 399.5, about 400 as I'd expect. 4.87 times 10 to the fourth. If I start moving my decimal point, I see I can move it 2 places, but not 4. I need to append a couple of zeros. So I can rewrite that as 4.8700. I can add more zeros to the right side after the decimal point. And now I have enough spots that I can move my decimal point 4 places to the right, making 48700. And then I'll stick commas in there to separate the groups, so 48,700. And lastly, 1.17 times 10 to the negative 3. Again, I want to move 3 places to the left, but I only really have 1 place to go. So I can append zeros to the left side in front of the decimal. So I can make this 001.17 times 10 to the negative 3, move my decimal point 3 to the left, and that makes 0.00117. Any questions on scientific notation? Okay, so that was how to move between decimals in scientific notation. And let's do a couple examples working with operations on scientific notation. So what if I want to multiply two numbers that are in scientific notation? Well, kind of nicely enough, 6 times 10 to the second, that's actually just the multiplication of two numbers. I mean, on one hand, I can think of it as a notation in and of itself, but really that notation is just representing one number times another, in this case 1.6589 multiplied by the number 10 to the fourth. So I really just have the product of two things multiplied by the product of two other things. That's really just like 6 times 10 squared times 1.5 times 10 to the negative 3. But multiplication is commutative. I can put my stuff that's not powers of 10 out front and my powers of 10 at the end. So I can have like 6 times 1.5 out front multiplied by 10 squared times 10 to the negative 3 at the end. 6 times 1.5, 1.5 of 6 is 9. And then here I have 10 squared times 10 to the minus 3. I have the product of two things that have the same base. I add the exponents. 9 times 10 to the power 2 minus 3, or negative 1. What if I want to divide numbers in scientific notation? Well, again, because scientific notation is just really the product of two things, it works really nicely with division as well. So if I have 9 times 10 to the negative 5 over 6 times 10 to the negative 2, I can really just think of this as like 9/6, right? If I have A times B over C times D, I can break that into, say, A over C times B over D. So I can think of this as 9/6 multiplied by 10 to the negative 5 over 10 to the negative 2. Or 9/6 is 1.5 times, and then I have 10 to the power. Well, my quotient rule, if I have base to a power divided by the same base to a power, I subtract the powers, the numerator minus the denominator power. Negative 5 minus a negative 2, or negative 5 plus 2 is negative 3, right? If I wanted to be a little more explicit about this, I could write this as 10 squared over 10 to the 5th, resolving those negative exponents, and I see 10 to the power 2 minus 5 is clearly 10 to the minus 3. This is already in scientific notation, so I can just leave it as is. Okay. So take a look at these last two exercises in this section. We'll take maybe 2 minutes or so to go through these. Take about 2 minutes, work through these ones, and then we'll finish up this section. Okay, so for the first one, we do a similar thing that we did up above. We take our numbers that are not powers of 10 and we maybe push them out in front. So I have 2 times 3.7, and then move our powers of 10 to the end. So times 10 to the negative 1 times 10 to the negative 3. 2 times 3.7 gives me 7.4. So that came from these two. And then 10 to the negative 1 times 10 to the negative 3, that's 10 to the power negative 1 plus negative 3, or 10 to the negative 4 power. And that's my answer. And then if we look at the second one, we can do something similar to what we did above. We have a quotient of two numbers that are in scientific notation. We can break the non-powers of 10 off out in front, make that 2 over 4, and then multiply by the powers of 10, that ratio, 10 to the third over 10 to the minus 1. 2 over 4 is 0.5. 10 to the third over 10 to the minus 1. I could either think of that 10 to the minus 1 coming up top as a 10 to the plus 1, making 10 to the fourth, or I could use my quotient property, 10 to the power 3 minus a negative 1, or that's 10 to the 3 plus 1, or 10 to the fourth. And I might think here, I just write 0.5 times 10 to the fourth, and I'm done. But the original numbers were phrased in scientific notation. I probably should answer in scientific notation. And if I look carefully, this is actually not scientific notation. What do I have in front of the decimal point? I have a 0. I don't have exactly one non-zero digit in front of the decimal point. So actually, I need to rewrite 0.5 in scientific notation. I need to move my decimal point 1 to the right, making 5. And then I need to account for that by multiplying by 10 to the minus 1. And then times 10 to the fourth. And I can regroup, right? This is like 5 times 10 to the minus 1 times 10 to the fourth, or 5 times 10 to the power negative 1 plus 4 is 10 to the third. So 5 times 10 cubed, or 5,000 is what we get here. And as kind of a side note, if we were to think of this a little bit differently, if I was to think of 2 over 4 times, well, 10 to the minus 1 on the bottom makes just a 10 to the plus 1 on the top, and then times 10 cubed, right? 2 over 4 is 1/2 times 10 gives me 5 times 10 cubed. So having worked out the answer, I can look back and see that there was, a little more efficient way to do it, but I don't think this would have been clear from the beginning. But this helped me kind of validate that this answer is the right answer. Or we can think of 20 over 4, 2 times 10 over 4, 20 over 4 being 5. Okay, so are there any questions on really anything in chapter 6? We're done with chapter 6 at this point, so we talked about monomials and polynomials and some operations on them, how to add, subtract, multiply, divide them, as well as some information about integer exponents, scientific notation at the very end here. Okay, so let's move on then to chapter 7. So chapter 7 on factoring. So one thing about factoring is, each course, especially in math, I'm not sure if this is so true in every discipline, but it seems to be true in essentially all math courses. There's kind of like, roughly in the middle of the semester, there's kind of like a hump topic, like you have a hump day, right? It's like some people say Wednesday's the hump day. Like if I can get over Wednesday, then Thursday and Friday are kind of, a little easier. There tends to be like a hump topic in most math courses. So in Math 80, that tends to be adding fractions with unlike denominators. Like if you can get that, if you really, put in the time and effort and drill those problems and really understand that material and do well on that topic, then the rest of the course is kind of downhill in the good sense. Like you're not like downhill as in it gets worse and worse, but in downhill in the sense that it's like you've crested the hill and you're walking down the other side and it's easier from that point on. So I think most of our courses have something like that. And in calculus, it's the kind of the famous chain rule. It's like the make it or break it part of the course. And I think in Math 90, it is really this chapter 7, factoring, and really the idea of factoring trinomials, which we'll see in a couple sections. So So my strong recommendation with this chapter would be to really take it seriously, to be very diligent about it. Um, spring break is coming up, so maybe even allocate a little bit of time over spring break, maybe a couple of days for a few hours to even go back and drill some of this material. Uh, Make sure that you really get this down. This is kind of the kind of make it or break it topic for the Math 90 course. If if you put in the work and the effort and the determination and really understand this material, then the rest of the course is kind of downhill in the good sense. But if you struggle with this material, if you never really put in that work, then the rest of the course is going to be a slog. So, um, so with that being said, some things you can do to kind of help you with that process are, number one, reading ahead. So we're covering 7.1 today. So make sure you read through section 7.1 in the book, and before Thursday, maybe take a read through 7.2. So reading ahead a little bit kind of primes you for what's going to be lectured on. It maybe brings up some questions that you might have. You might say, wait, I saw them do this in the book. I'm not exactly sure why that worked that way or why they chose to do this way instead of that way. Um, and with, you write that question down in your notes, and then maybe you get that question answered during lecture. Maybe just as I'm going through, I answer it, or maybe I don't answer it and you ask the question and then you get an answer that way. So reading ahead is a great tool. You don't have to read ahead. If you read ahead to section 7.2, you don't have to be an expert in 7.2 before the lecture. Of course not. Then why are we having lectures? But reading ahead, kind of skimming 7.2, taking some short notes, maybe working through a couple of the examples that they do, just kind of writing down line by line what they do and trying to see how everything connects together really primes you to receive the material a lot better. So reading ahead, I think, is one big thing that you can really do to put yourself ahead of the game. The second thing is setting aside time each and every day, at the very least each weekday, maybe Monday through Friday, to work on problems, right? So don't come to the homework on Sunday evening when it's due at 9 p.m. and then do like a 3-hour slog to try to get through everything in a rush as fast as you can. You're really not going to learn very much that way. You're not going to retain any of that material. But if you say, okay, Monday through Friday, I'm setting aside an hour and a half each day, every day, it can be different times each day, whatever, but if you can, if you can say whatever, 12 to 1:30 every day, Monday through Friday, I'm going to sit down and work on the chapter 7 material, maybe choose some problems from the book to drill, maybe work on the homework, something like that. Maybe things like rewrite notes or rework the examples and exercises in the notes. But if you're consistent like that, um, you know, that kind of consistency is going to get you further than putting in twice the amount of time all in, say, a big lump. And the third thing related to that is I really think that there's just no substitute for time on task, right? Working in a field at the edge of your competency. So not drilling things that you can do in your sleep, not things that you've mastered already and really know how to do, and spending 3 hours doing that. That's not going to get you very far. It'll help a little bit maybe, but it's not going to get you too far. But working at the edge of your competency, working on problems that are challenging that maybe you don't know how to do, maybe you have to you try it once and you end up with the wrong answer and you have to go back and fix your work and to get the right answer, right? It's a little bit like exercising, right? If you're like lifting weights and you're lifting 2-pound weights, well, you're probably not going to get much stronger, right? You have to kind of lift weights that are hard for you to lift in order to actually get that adaptation to get stronger. So, and I mean, believe me, I've tried to find every cheat myself, like how to gain mastery in less time, and becoming more and more and more convinced that it really just does come down to time on task, focused time on task, not again, kind of put your phone away, like forget about the everybody being able to reach you at all times. So focus time on task at the edge of your competency. I really think that there's no substitute for that. Whether it's, learning math or learning to play the piano or, working out to get stronger or whatever it is that you want to accomplish, focus time on task at the edge of your competency, is I don't think there's any substitute for that. I don't think that you're gonna, find just the right YouTube video or just the right professor or just the right textbook or whatever it may be that it's going to say it in just the right way. And in 12 minutes, you'll be an expert in factoring. I don't think that such a thing uh, exists. So focus time on task, working at the edge of your competency, and doing that consistently, day in and day out, even for a shorter period of time. Even if you can only do 45 minutes a day, doing that 45 minutes a day for 6 days a week is going to be better than doing 10 hours, on Sunday from 2 p.m. to midnight or something, trying to grind through all of your homework all at once. Okay. All right. So end of rant, I suppose. But yeah, so chapter 7 factoring, go into it taking it seriously, and it's going to be manageable. Okay, so section 7.1, finding the greatest common factor and related to that factoring by grouping. So we're going to start by just finding the greatest common factor. And let's actually just look at the greatest common factor of 3 numbers. So what do we mean when we say the greatest common factor? Well, let's actually even take 3 simpler numbers as a demonstration. Maybe I have the numbers like 6, the number 12, and the number, I don't know, 24, something like that. These numbers have factors, right? 6, I could list out its factors. 1, 2, 3, and 6. So for an integer, for a positive integer, its factors, or a number is a factor if it divides evenly into it. So 6 divided by 1 is 6. 6 divided by 2 is 3. 6 divided by 3 is 2. 6 divided by 6 is 1. Or in other words, I could break 6 into 1 times 6. So I write 1 and 6 down as factors. I could also break 6 into 2 times 3. So I write 2 and 3 down as factors. Similarly with 12, 1 is always a factor. 12 is 1 times 12, or 2 times 6, or 3 times 4. And 24, it's going to have a bunch of factors. 1 times, I might actually write it this way, 1 times 24, 2 times 12, 3 times 8, 4 times 6. 5 doesn't divide evenly into 24, and if I get up to 6, well, when I start counting up from 6, I'm kind of repeating these other factors, 6, 8, 12, 24. Now I see that these numbers have some common factors. For instance, 1 is a factor that is common to all 3 lists, 6, 12, and 24. 2 is also a common factor. It's common to all the lists. It's in all of the lists. It's common in that sense. 3 is also a common factor. Maybe I'll write it like, diamond. 4 is a factor that's in some of them, but not all of them, so it's not a common factor, right? The same with 12 or 8 or 24 is in some, but not all of them. But I actually also noticed that 6 is a common factor. So I've now indicated all of the common factors, 1, 2, 3, and 6. And I'm asking, what is the greatest common factor? What is the greatest common factor of these 3 numbers? The common factors between these 3 numbers are 1, 2, 3, and 6. What's the greatest of those numbers? 6. That's the idea of the greatest common factor. What's the procedure for finding a greatest common factor? I mean, I certainly, for numbers like this, I don't want to write out all of the factors and look for all the common factors and list them and then find the biggest one. That's a very cumbersome and tedious process. So what's the efficient process for finding the greatest common factor? Well, for finding the greatest common factor, let me actually just push this down here a little bit. Let's revisit the 6, 12, 24 example. I'm going to take the number 6, and I'm going to write out its prime factorization. So 2 times 3. I'm going to take 12, and I'm going to do the same. So 12 is 3 times 4, or 2 times 2 times 4. Or 3 times 4, 2 times 2 times 3, or 2 times 3 times 2. And 24 is going to be 2 times 12, or 2 times 3 times 4, or 2 times 3 times 2 times 2. So I write out the prime factorizations, and I keep kind of the primes like lined up in their columns. So the first factor of 2 is all lined up above one another. The first factor of 3 is lined up above one another. The second factor of 2 is lined up. The third factor of 2 is lined up, and so on. Something is common if it is in all 3 of them. So I look for prime numbers, like the first factor of 2, that is common to all 3. Since all 3 of them have at least one factor of 2, I write that 2 down here. I notice they all have at least one factor of 3 as well. Since this column is filled in for everybody, I write a 3 down. The second factor of 2, well, 12 and 24 have that, but 6 doesn't. It's missing that. So I can't write the second factor of 2 down or the third factor of 2 because the 12 and the 6 are missing that one. So 2 times 3 equals 6, and that's our greatest common factor. We write out the prime factorizations, keeping our columns nicely aligned. Any column that is completely filled in, where I have that prime number represented in every one of my inputs into the greatest common factor, I write that as a component of the greatest common factor, and at the end I just multiply them together to get the answer. Okay, so let's do that process on numbers that are a little more challenging. 117, 39, and 78. So what's the greatest common factor? Well, let's start with 39, and then 78, and then 117. So 39 is, well, I think that's 13 times 3. 78 is 39 times 2, or that's 3 times 13 times 2. And if you didn't realize this, you might see, okay, well, 9 plus 3 is 12. I can do a divisibility test for divisibility by 3. 12 is divisible by 3, so 39 is divisible by 3. Divide 39 by 3 and get 13. 78 we see is divisible by 2 because it's an even number. 78 over 2 is 39, and then there we go. 117 might be a little harder. But I do know that 7 plus 1 plus 1 is 9. And 9 is divisible by 9, so this should be 9 times something. 9 times 10 is 90, times 11 is 99, 12 is 108, and I think 9 times 13 is 117. 108 plus 9 is 117. So 117 should be 9 times 13. 13 is prime, but 9 is 3 times 3. So 117 has a first factor of 3. It has a factor of 13. And then it has a second factor of 3. And I noticed that the first factor of 3 column is represented in all 3 of our factors here. The factor of 13 column, that's represented in all 3 of them as well. The factor of 2, well, it's in the 78, but not the 39 or 117. It's not common to all of them. The second factor of 3 is also not common to all of them. We only have a second factor of 3 in 117, not in the other two. So my GCF is 3 times 13, or 39. In other words, 39 is a common factor to all of these. 39 is 39 times 1. 78 is 39 times 2. And 117 is 39 times 3. So 39 is a common factor to 117, 39, and 78. Furthermore, it's the greatest common factor. If I tried to multiply anything else on there, like if I tried to multiply, say, a 2 on the 39 to get a 78, well, that 2 isn't like a building block of 39 or 117. It doesn't have any of those 2s. So that, that extra 39 times 2 is not going to be a factor to 39 or 117. So this is one of the reasons that like math folks like prime numbers so much, is they're kind of like the building blocks, almost like the Lego blocks to build all of our different numbers up, and they can be quite useful. So we're breaking things down to kind of their component Lego building blocks, and then seeing, between these three Lego sets, what are the common blocks? And then we build what we can out of those common blocks, and that's our greatest common factor. Okay, so how do we approach something like a greatest common factor of, say, three monomials? Well, again, I can look at this and say 42x to the fourth, 14x to the fifth, and 84x to the sixth. I can kind of write down their prime factorizations. I can do that for the number part. Let's do that first. 42, well, that's like 7 times 6, or that's like 2 times 3 is 6 times 7. Just doing the numbers right now. We'll think about the x's in a minute here. 14 is 2 times 7. And 84, well, I see that 84 is even, so it's going to be 2 times something. 2 times 42, or 2 times 3 times 7 times 2. And I see that, again, just think about the numerical part. I didn't do the x's yet. Just thinking about the numbers, I see that the first 2 and the 7 are common to all three. The 3 is not common to all three. The 14 is missing it. And the second 2 is not common to all three. I can actually make this maybe a little bit more efficient. A little more efficient in terms of writing stuff out, but also a little more efficient in terms of my thought process. I could write 84 as 2 squared times 3 times 7. I could do that, right? There's nothing wrong with that. And if I really wanted to force the issue, I could write 14 as 2 times 3 to the 0 times 7. And it's kind of a silly way to write it, but I suppose I could write it that way. 3 to the 0 is just 1. And then in my greatest common factor, really kind of what I'm doing is I'm taking each of my prime factors that I see popping up, 2, 3, and 7, and I'm raising them to the power that is the smallest power that I see written there. So in my 2's column, I have 2 to the first, 2 to the first, and 2 to the second. What's the smallest power? Well, the smallest power is 2 to the first. In my 3's column, 3 to the first, 3 to the 0, 3 to the first. What's the smallest power? 0. In the 7's column, well, everything is just 7 to the first, so 7 to the first. Or this is just 2 times 7, or 14. I could have done that up here. Right, let me see if I can just get rid of these circles. I could have done that up here and chosen to write 2 to the first times 3, 2 to the second times 3, and 2 to the third times 3, and not had these 2's over here. And then when I say, okay, in my 3's column, everything is just 3 to the first, so I have 3 to the first. In my 2's column, I have 2 to the smallest power of 1, 2, and 3. That's just 2 to the first. Hey, that still works, right? This is just a more concise way of doing the method that I was doing before. Or if I looked at the second example here, well, I have 3 times 13, 3 times 13 times 2. There's nothing much I can do with those. But this 3 times 13 times 3, I can really write as 3 squared times 13 and get rid of this extra 3 over here. This is a lot cleaner, a lot more concise. And then again, I have my 3's column. It has powers of 1 and 2 popping up above. I take the smallest of those, 1. My 13's, they're all 13 to the first, so that's 13 to the first. My 2's column, really I see I have like 2 to the first, 2 to the 0, 2 to the 0. This is like 2 to the 0. I put 2, and what's the smallest power? 0. I still have 3 times 13 as my greatest common factor. And this might be reminiscent of something to you. If you think back to adding fractions with unlike denominator, we had to find the least common multiple, or the lowest common denominator, or least common denominator, or lowest common multiple. I don't know. And for that, what we did was we did a similar process, but instead of taking the smallest power, we took the largest power for each column. So the GCF just takes the smallest power for each column. But now with this generalization, I think we can see really clearly what we do with the x's now. So 42, I break that into its prime components, 2 times 3 times 7. X to the fourth, I can't really break that down anymore. It's just like 4 X Lego building blocks that are sitting there, right? You can't, break that down into something simpler. So it's just X to the fourth. I have 4 factors of X here, 5 factors of X here, and 6 here. So I'd also like to represent my X column. I have some different powers attached to my X's, 4, 5, and 6. What's the smallest power I see? The 4th power. So it's looking at it this way with the powers and picking the smallest power, I think makes it very clear how to move to the X's. Now I could look at this the old way and write a whole bunch of X's out, right? And see which columns are fully represented and all of that. But I think we can agree that at the very least, that's tedious, if not very confusing when we get to the X's. And now I see that I just have 2 times 7, well, 2 times 1 times 7 times x to the fourth, or 14 x to the fourth is our GCF. Shouldn't write it that way. GCF equals, I guess. What do I mean by this? I mean that 42x to the fourth, there's 2 times 7x to the fourth times 3. So 42x to the fourth can be written as 3 times 14x to the fourth. 14x to the fifth, there's my 14. And x to the fifth is like x to the fourth times x. So it's like x times 14 x to the fourth. And what is 84x to the sixth? Well, it's 14, which is 7 times one of the 2's, times 6, 2 times 3, the other 2 times 3. And x to the fourth times what gives me x to the sixth? X squared. Right. So in other words, what I'm saying is basically I have monomials with integer coefficients that I start out with here. I can like pull off a 14x to the fourth from each of them, and in each case be left with a monomial with an integer coefficient. That's 3 in the first case, x in the second case, and 6x squared in the third case. What if I have multiple variables? So 3x squared y cubed. And as an aside, there's nothing special about having 3 things that I'm getting the GCF of. I could get the GCF of 2 things or of 5 things or of as many things as I want. So if I have these 2 monomials, 3x squared y cubed and 12x y to the fifth, let me do the numbers first. So 3, while its prime factorization is just 3, we'll write it as 3 to the first. 12 is 3 to the first times 2 squared. 3 to the first times 2 to the 0, I guess, if I really wanted to be pedantic and, be very clear about what's going on here. Then in my monomials, so that takes care of my number part of the monomials, all the building blocks for the numbers. I have some building blocks for the variable parts as well. I have some X building blocks and some Y building blocks, right? Some like blue Legos and some yellow Legos or something. I have 2 factors of X versus 1 factor of X and 3 factors of Y versus 5 factors of Y. My GCF is going to be 3 to the power, the smallest power that I see. Both powers are 1, so it's just 3 to the first, times 2 to the power, the smallest power I see. Well, the powers are 2 and 0. Smallest is 0. Times x, the next building block, to the smallest power I see, which is 1. Times y, to the smallest power, which is 3, the smallest of 3 and 5. My GCF then is 3. 2 to the 0 is 1, so that's just 3. X to the first is just x. Y cubed. And again, what am I saying here? I'm saying that this is a common factor to both of these and that there's no bigger common factor. I'm saying that 3x squared y cubed can be written as 3xy cubed. There's 3, one of these x's, and then y cubed times x. And 12xy to the fifth, well, that's 3xy cubed. So there's my 3, there's my x, and then 3 of these y's come into the y cubed, leaving me with 4y squared. Between 4y squared and x, there are no other common factors. I could not have gotten a bigger common factor than 3xy cubed. And it is 3xy cubed is a common factor to both of these. As I can see, I can split it off and it leaves me with monomials with integer coefficients. Okay, so let's look at an exercise here. Find the GCF for each of the following lists. So we'll take maybe actually about maybe 7 minutes to do this. I think the first one should go pretty quickly. So we'll do about 7 minutes, work through these, follow the more concise and efficient method up here. The original way that I kind of did it, writing all of this stuff out, was just to kind of demonstrate the point and lead up to the final method. So use the more concise and efficient method for all of these and take about 7 minutes, and then we'll come back and discuss the answer. Okay, so it's quite a bit of writing for these three, but hopefully you all at least kind of understood the strategy. If it if you didn't quite go through as quickly as I did, if it would take you a few minutes more than 7 minutes, that's perfectly okay if you didn't quite get to the very end. But hopefully the strategy was at least clear. So for 60, 40, and 100, we see the prime factorization for 60 is 2 squared times 3 to the first times 5 to the first. For 40, 2 cubed times 3 to the 0 times 5 to the first. And for 100, 2 squared times 3 to the 0 times 5 squared, if we really wanted to put the 3 to the 0s in there. And our GCF then, how many factors of 2 should we have? What's the smallest power on 2? We have powers of 3 and 2. The smallest of those is 2, so 2 squared. For the factors of 3, we have basically a 3 to the 1, 3 to the 0, and a 3 to the 0. If we don't see a 3 popping up, we can just omit it and not write it and remember that that's a 3 to the 0 power. So we get 0 factors of 3, 0 powers of 3, right? 3 to the 0 power, smallest power is 0. And then for our factor of 5, we see that we have powers of 1 and 2, so 5 to the first is what ends up in our GCF. So we get 2 squared times 3 to the 0, or just 1, times 5. 4 times 5 is 20. And of course, 60 can be written as 3 times 20, 40 as 2 times 20, and 100 as 5 times 20. So we see it's a common factor to all three, and nothing bigger than 20 would still be a common factor of all three, 60, 40, and 100. And then we follow a similar process for this next part. We have a similar idea with the numbers, 66, 18, and 36, but now we just have x to the fourth, x to the fifth, and x to the sixth as well in our three components of our list. So we'll start by breaking down the numbers into their prime factorizations. That's usually the kind of logistically most challenging part of this whole process, is dealing with the numbers, the numerical coefficients. Because I mean, x to the fourth pretty clearly is just 4 factors of x, but 66, what's its prime factorization? There's lots of numbers, there's lots of building blocks that could be components of 66. So 66, we can think of just chipping away at it. Maybe we recognize it as 33 times 2, or maybe 6 times 11, or something like that. 2 is prime. 33 seems to be 3 times 11. So 2 times 3 times 11. Now we do have a list of prime factors. So 66 is 2 times 3 times 11. Or I'll come back over here. 2 to the first times 3 to the first times 11 to the first power. And then we can plug on our x to the fourth at the end. That's there as well. For 18, maybe we recognize 18 as 6 times 3 or 9 times 2, but 6 times 3 is 2 times 3 times 3, or 2 times 3 squared. So the 18 coefficient is 2 to the first times 3 squared, and then times x to the fifth. If I really wanted to, I could note that there are 0 factors of 11. We don't have the 11 factor showing up in 18, the one that showed up in 66. So if I wanted to be very explicit about everything, I could write out 11 to the 0. Or if I was okay with just kind of keeping that in the back of my mind, I could leave this blank as long as I don't mistakenly end up writing an 11 to the first down in my GCF. I need to remember that there's a missing 11 there, so that's really 0 factors of 11. And then my x to the fifth at the end. And then for my third, 36, maybe I recognize a 6 times 6 or 9 times 4, something like that, factors into 2 squared times 3 squared. So 36 is 2 squared times 3 squared, and again, I can write 11 to the 0 if I really want to. And then my variable part times x to the sixth. And now I see all of my building blocks that could pop up, 2, 3, 11, and x. How many factors of each of them should I include? The powers of 2 are 1 and 2, and the smallest of those powers is 1, so 2 to the first. Similarly, for the 3's, I have powers of 1 and 2 on the 3's. The smallest of those powers is 1, so 3 to the first. For the 11's, I have powers of 1 and 0. The smallest of those is 0, so 11 to the 0, or just don't end up with any factors of 11 in the GCF. And then for x, I have 4, 5, and 6 as the powers. The smallest is 4. So 2 times 3 times x to the fourth, or 6x to the fourth, is my GCF. And as I kind of indicated here, 66x to the fourth is 6x to the fourth, my GCF, times 11. 18x to the fifth is 6x to the fourth times 3x. And 36x to the sixth is 6x to the fourth times 6x squared. So I can break off a 6x to the fourth from each of these, and I'm still left with a monomial with an integer coefficient times x to a non-negative power. And the just 11 up here, I think of this as like 11x to the 0 power. But I don't want to end up with like fractional numbers or like negative powers on x. That's what I'm not looking to end up with. And then lastly, my GCF of 35xy to the fourth and 25x cubed y squared. I do something similar. 35, the number breaks down into 5 times 7, and those are both prime, so that's my prime factorization. 5 to the first times 7 to the first. 25 is just 5 squared. 5 is prime, so I could write that as 5 squared times 7 to the 0 if I wanted to just make sure that I remember that there are 0 factors of 7 and 25. And then I also have some x building blocks and some y building blocks. So I put an x to the first, y to the fourth, or an x cubed, y squared in my two lines. And then I can ask how many of my 5s, 7s, x's, and y's do I need to put into this mix to make my GCF? The powers on 5 are the first power, and the second power, the smallest of those is 1, so 5 to the first. On 7, that's like 7 to the first power versus 7 to the 0 power. The smallest of those powers is 0. 7 to the 0 power is what ends up in the GCF. X is, again, just x to the first. My powers are the first power, the third power, the smallest is the first power. So I just have one factor of x, or x to the first, in the GCF. And on my y's, I have 4 and 2 as the powers. The smallest of those is 2. So I have 5. 7 to the 0 is just 1, xy squared. And I might note that 35xy to the fourth is 5xy squared times what? Times 7, kind of what's left over, times 7y squared. And 25x cubed y squared is 5xy squared times 5. 5 times 5 makes the 25. X times x squared makes the x cubed, and y squared is accounted for. So in both of these, I can break off a 5xy squared factor, and I'm still left with a monomial with an integer coefficient. And I can't break off any more numerical factors. 7 and 5 don't share any common factors. And I can't break off any more variables. I don't, my second one has some more x's, but my first one doesn't have any extra x's to break off. And similarly with the y's, my first one has extra y's, but the second one doesn't have any extra y's that I could accumulate into that factor that I'm pulling out. So that 5xy squared is indeed my greatest common factor. I couldn't have gotten anything bigger out that would have still been a common factor. Any questions on anything from today? So again, I'll probably harp on it for the next couple of classes, but strongly recommend reading ahead, reviewing section 7.1, reading ahead to the second half of 7.1, and skimming 7.2. Again, you don't have to read with the intent to master the concept before the lecture, but reading so that you get an idea of what's going to be covered. Maybe if you have questions pop up, maybe if something doesn't quite make sense, it primes you for the lecture much, much better. And then trying to be diligent, at least for these next couple of weeks, about taking time every single day, at least, say Monday through Friday, or if some days don't work great for you, pick a certain, say 5 days per week, and spend 45 minutes, an hour, something like that, every single day, working on problems, drilling problems, going through exercises and examples from the notes, going through problems in the book, going through the web assigned homework problems, um, and really hitting that material every day like that is a much better way to go about it. So take care with this chapter 7. And when we get over chapter 7, you'll be in great shape for the rest of the course. Okay, so with that being said, I will stop the recording